Greetings everyone, and welcome to my next video in my little lecture series on applied differential equations. In this particular video, we're going to be solving a homogeneous system with complex eigenvalues. So these are homogeneous systems of linear d's. So let's get started on the answer. If we are to write out our matrix A, remember that what we've got is we've got vector x prime is equal to A onto vector x, where vector x is just column vector xy, where A is then equal to, and then now we just write down the coefficients on x and y, 1, 1, and then -2 and -1. And we want to find the eigenvectors and eigenvalues for this matrix. So in order to do that, we say that the determinant of A minus lambda I is equal to 0. So we're going to get 1 onto 1 minus lambda and -1 minus lambda on the main diagonal. The off-diagonal elements are going to remain the same, 1 and -2. That's going to equal 0. When we write this out, we get 1 minus lambda, and now I'm going to multiply it by -1 minus lambda, but to make it easier on myself, I'm going to pull out the negative, and that becomes 1 plus lambda. And then subtract the off-diagonal product of the off-diagonal elements. We're subtracting a -2, so we're going to get plus 2 is equal to 0. If we multiply this through, we get negative onto 1 minus lambda squared plus 2 is equal to 0. That means that when we multiply through, we're going to get a -1 plus lambda squared plus 2. That gives us lambda squared plus 1 is equal to 0, and that gives us lambda is equal to plus or minus I. Now, note that we generally write this in the form lambda is equal to alpha plus or minus beta I, and so here we've got that alpha is equal to 0 and beta is equal to 1. Okay, so we're going to let lambda 1 is equal to I. Fortunately, these come in conjugate pairs, so we only had to find one of the eigenvectors, and then the other eigenvector will just be the conjugate of that. We're going to take A minus lambda I, where I is I2, it's the identity matrix, times K is equal to 0. And basically what we're going to take is we're going to take the matrix A and subtract 1 from all the main diagonal elements. So you get 1 minus I and -1 minus I, 1 and -2 here. That becomes our augmented matrix. And we're going to RREF this guy. If we REF it, actually the easiest way to go is to swap the two rows. And then take that, the bottom row there, it's now in the top, and divide by -2 everywhere. We get 1 and then 1/2 onto 1 plus I and 0, and then the bottom row just becomes all zeros. And then y is our free variable, so we're going to let y equal t. Then we can see that x is going to be the negative of t times the y entry, so it's going to be -1/2 onto 1 plus I times t. And then our vector k, eigenvector here, k1, is going to be -1/2 onto 1 plus I, and then 1 in the bottom row. And that's kind of a little bit messy, so I'm just going to scale it and multiply it by 2. And get -1 minus I in the top and 2 in the bottom, like so. And we know from applying the complex conjugates that we've got that lambda 2 then is equal to the complex conjugate. It's equal to -I, and our k2 is a complex conjugate of k1 is -1 plus I, and 2 also as a column vector. Okay, So now that we've got that, we have to figure out B1 and B2. B1 is the real part of K1. It's going to be -1, 2, like that. B2 is going to be the imaginary part of vector K1, and it's going to be -1 and 0 because of the, if you look up here, here's K1, so the real part is the -1 and 2, and the imaginary part is just the -1 on the top row, and there's nothing on the bottom. And now we write out that x1, I suppose I should make a nice big capital letter, is equal to b1 cos beta t minus b2, that's a vector over b1, minus b2 sine beta t. We found earlier that beta was equal to 1, so this is just going to be a -1, 2 cos t minus -1, 0 sine t. x2 is going to be b1 sine beta t plus b2 cos beta t. So that's going to be -1, 2 sine t plus -1, 0 cosine t. And the general solution is capital X is equal to C1 x1 plus C2 x2. We get capital X. Don't know why my pen doesn't like to do that first stroke for some reason. It's going to be C1 onto what we've just written before, cos t, and then that column vector sine t plus C2 -1, 2 sine t plus column vector -1, 0 cos t. And if you like, you could tidy it up a little bit, multiply out some vectors, collect stuff, and then you get the column vector. So C1 times column vector sine t minus cos t. That's not two entries, that's a single entry over 2 cos t plus C2 onto negative sine t minus cos t, and then 2 sine t in the last row. And there we are.